So, kinetic and potential energy. It was fun talking about this yesterday. We're going to keep going with this discussion today. So let's take a look at the question, and then we'll see if you had any questions on the homework. When there's a big earthquake, tons of energy is released. That's why buildings fall over and glass breaks everywhere. So, in what form did this energy exist before the actual earthquake happened? If you had to identify one of those energies, potential, spring potential, or kinetic, what form did it take before the actual earthquake happened? Potential, gravitational potential, or spring potential? Okay. I'd probably say spring potential myself. What I'm thinking of, because you guys know about how the plates move and stuff like that from geography. So, like, if the plates are maybe going like this, or one's going up and one's subducting down, it's not a smooth motion. You know, it's kind of jerky. And so, as one plate's trying to go up, eventually it just kind of gives a little bit and it jerks a little bit. And so that's when you get those earthquakes happening. So it's kind of, you can kind of think of it like a spring, you know, building up that strength, and then it's released, and then it moves suddenly like that. Kind of like if you're stretching a spring and then you let it go and it moves. So that's how I would think of it. If you think of it as gravitational potential energy, maybe you guys have an explanation for that. What are your thoughts on where that came from? Anybody?
I didn't know what spring was.
Oh, okay. Yeah. Okay. Yeah, so even though, you know, plate motion doesn't take actual springs into account, you can still have spring potential energy under those conditions. So, okay. Questions on the homework? Anything you'd like to go through? Going once. Going twice. Let's at least take a look at one of them here.
For number 6.
Okay.
When it's like right at the top, like the maximum height.
Sure.
Would that just be potential energy?
Yes, it would be. Yeah, for number 6, you'd have spring potential energy at the beginning, but you just label it as regular potential energy. We're not specifically making those distinctions until we get to the notes today. But then, yeah, when it's on its way up, you've got both potential and kinetic, and once you get to the very top, it is all going to be potential. What about number 7? We'll do this one, and then we'll just kind of collect it and then do some notes. So we have this piece of clay. It starts up, and then it drops, picks up speed, and then splats on the ground. So for the first part, when it's in the air, what kind of energy does it have? Potential, absolutely. When it's halfway down, what does it have? Absolutely, potential and kinetic. And then when it's splat on the ground, what sort of energy is present there? None. That is correct. Because when it's on the ground like that, if it's not going to ricochet back up, it has then transferred all of its energy into the ground. And that transfer is something we're going to look at more closely today. That would be through heat. Okay. I'll just, yes?
For 8, would that just be, like, since it's just, like, with that, is it going to keep going forward since it's frictionless?
Well, if it's coasting, it'll just keep that same velocity the whole time. So, because it would keep that same velocity, I'd say that the kinetic energy just stays the same through all of those.
Yeah, I just put, like, circles with half and half through, like,
For number 8?
Yeah.
Okay, half a kinetic, and what's the other one?
Potential, because, like, it's always going to...
You could, if you were thinking of it like the engine and the person being off the ground a little bit, that's one way you could say that there's potential there. And, you know, the center of mass of the truck is definitely, you know, a ways off the ground. For me, I probably would just put kinetic energy for the whole thing. But that's not a wrong interpretation by any means. Okay, I'll come around and get this from you. All right, so let's just do some notes today, and then you'll have a good amount of time to hopefully get through the homework, just like last time. You can title your notes today, Energy Flow. Energy Flow. Couple things we do have to make sure we're aware of as we go into this topic. We have to make sure that we know what the abbreviations are for the things that we talked about yesterday. How do we abbreviate potential energy? PE. Maybe I'll put those over here. Now, if you were looking at potential energy in a textbook, usually it's abbreviated with the capital U. One of the reasons I don't really do textbooks much. Just for some reason they have an aversion to using 2 letters for an abbreviation. And they can't use capital P because it's used for power and momentum. So, anyway, that's potential energy. Spring potential energy, what do we use for that? Yeah, PE with a little s. You can make yours cursive or you can make yours regular, whatever. Kinetic energy, of course, is KE. The other things we have to make sure that we're aware of are the ways that we can gain and lose energy. Anybody remember how we can gain energy? Work. Yes. Maybe you start with no energy. If that's the case, you have to perform work on that object in order to get it moving or raise it above the ground to give it potential energy. We abbreviate working with capital W. W is an interesting letter, isn't it? It's like the only letter in the alphabet that takes more than 1 syllable to say. How is it possible that 1 letter can take 3 syllables to say it? My name has 3 syllables, and it's got 11 letters in it. So, W is going to be working. What's one way that we can lose energy? Heat. And that's abbreviated with the letter Q. That's something we do have to get used to. And then the last one is going to be radiation, or if an object is radiating light. Vibration would go into heating. So those are the things we have to be aware of as we go forward with this. Hopefully that's pretty review. So basically we're just going to go through about 3 examples and then you can work on the worksheet. W doesn't even look like 2 U's, does it? It's like 2 V's. It should be double V. Just ripping on the letter W today. Okay, let's take a look at how we're going to deal with some of these problems on the worksheet with energy flow. The first example, when was the last time any of you guys were out roller skating or rollerblading?
5 years ago.
5 years ago? Nice. Anybody still do it once in a while? Maybe just 1 or 2. I hadn't been out rollerblading since, well, same thing, like when I was a senior, maybe 5 years before that, 6th, 7th, 8th grade. So then I actually got back into it a little bit 2 or 3 years ago. My wife and I bought some skates, and we got back out there, and it was really fun. I missed that. So we'll say that this person is at a roller rink. This is a very special roller rink because it has springs attached to walls. So this person is on his roller skates. We've got a compressed spring right here. And at the beginning, he has a velocity of nothing. Eventually, that spring is released and he starts moving pretty fast. At that point, of course, his velocity is not equal to 0. His head also appears to have gotten bigger. So for this scenario, we need to do a couple things. We need to figure out what energy was present at the beginning, and we need to figure out what energy was present at the end, and what happened in between those two things. So the way that you'll be dealing with this on the worksheet is you'll have a little bar graph that you have to fill out. One for the original energy, one for the final energy. And these bar graphs are nothing spectacular. They're just labeled the same way with 3 different kinds of energy. On the worksheet, it starts with kinetic. So you'd have kinetic, potential, spring potential. And all you do is that for each of these scenarios, beginning and end, you would just put a little bar next to where the energy is. So what is all the energy at the beginning here? Spring potential, absolutely. So my original energy would just look something like this. I'd put a bar going all the way up under spring potential energy. Of course, if it was between 2 different things, you'd have bars that were about half that size in each. And at the end, what is all that energy transferred to? Kinetic, precisely. So that's how you would deal with that part of it. Now for the energy flow, what you're doing is you're starting from the beginning and you're just seeing how that energy changes as time goes on, not just beginning and end. So for the energy flow here, we start with spring potential energy. And after each, piece of energy that you have, you're just going to put a little arrow. That indicates you're moving on to the next one. Now, for this scenario, there is probably a small amount of time where this spring is unloading itself and moving you quickly, and you're moving. So there would be a small amount of time where you're going to have both spring potential and kinetic. You can throw that in if you want. I'd say that's kind of optional here. When you step back and look at the big picture, you've really got 2 things. You've got spring potential, and then you've got kinetic. So this is a very easy energy flow diagram. You'll see other examples in the next 2. Questions so far? Wonderful. Let's keep going. Here's our next scenario. So this guy is determined to get up this ramp, up to this point anyway. He starts at rest, and then he begins walking. He walks all the way up, and then he stops when he gets to this location. So what is the energy that he has at the beginning? Nothing, because he's on the ground, so there's no potential. There's no spring, so there's no spring potential energy. And he's not moving, so there's no kinetic energy. So originally, there is no energy here. You would have nothing in your bar chart. At the end, he is at rest, he's above the ground, and there are no springs. Precisely, potential. So that's what your bar graph is going to look like. Now we got to look at the energy flow, because there are a couple things going on here aside from just those two beginning and ending energies. If we start with no energy, what do we got to do anything? Work. Because work is a way that a system can gain energy. If you have no energy when you're at the bottom of this hill, you're not moving, there are no springs or anything, you have to do work on yourself in order to get yourself to start moving. Your muscles have to do work. So for the energy flow, it would start with work, and then as you walk up this ramp, you're going to have both kinetic energy and potential energy, and eventually you reach your final location here when you stop moving. At that point, all of your energy is going to be potential. And that's what we have for that. Easy enough, right?
Yeah.
Good. One more. Okay. This person is laying down at rest on a bright summer day on the top of a hill, just relaxing up there. Eventually, he nudges his way over to the edge of that hill, rolls all the way down, and comes to rest at the bottom. So the original velocity on Green Hill here is 0. The final velocity here on Green Hill is 0. So, let's think about what this means. What is the energy at the beginning?
No.
It is going to be potential. If you did want to define this as like the 0 point for the ground, yeah, your potential energy would be 0. But because you can move just a little bit this way and then go downwards, I'd probably say this has potential energy to it. Like usually we say if an object is released and doesn't go anywhere, that there's no potential energy. This would kind of be an exception to that. It's not a hard and fast rule. He can nudge his way to the edge of this hill and then allow himself to roll on down. When was the last time you rolled down a hill?
In a while.
Maybe about the same time you went skating last? Okay, so at the beginning, we've got potential energy. What kind of energy do we have at the end? Nothing! It is all gone. Because you reach the bottom. You're not moving. There's no kinetic energy. You're at the very bottom. There's no potential energy. And there's no spring down there. So there's no spring potential energy. So let's think about what's going to happen with our energy flow then. We begin with the potential energy that we have here. Any thoughts on what comes next? Good guess. Looking for something different though. W, why? Yeah. In order to get to the edge of this hill, he has to do a little bit of work on himself in order to do that. So some work is performed. He's adding some energy to his system. And then he begins tumbling down, and that's where what Gavin said would come into play. So we've got kinetic energy and potential energy. And the reason for that is because he's off the 0 point here. He's above the ground. And as he goes down, he's also moving. So he's got both potential and he's got kinetic energy. Eventually, though, he reaches the bottom. And once he reaches the bottom, all of that energy is going to be gone. Where did it go? Heat! Precisely. Yep. Unless he starts on fire, then it would be radiation. Generally, that doesn't happen, though. So, this is energy flow. Questions on this? Alrighty.
Wait.
Yeah.
So, it has to start on fire to be radiation.
Or you could just light up in some other way.
Oh, okay.
If you naturally glow in the dark, you naturally would be losing energy to radiation.